Hello, class. So we are going to pick up here at the second slide in chapter 5 about thermodynamics. Hopefully you read the introduction, so we're all on the same page. You know what the laws of thermodynamics are, and you know what your goals for this chapter are. Okay, so we're going to explore a little bit more about potential energy and kinetic energy. So in the simulation that I showed you in class, we looked at a girl on a bicycle, and the potential energy in that image was the food that she had eaten. And the kinetic energy was her feet moving to turn the wheel of the bicycle, which was turning the wheel, generating energy, electrical energy. Okay, so that's all different kinds of kinetic energy. And then that electrical energy got transformed into electrical energy to heat up the water in our beaker. That's thermal energy. So we can transform energy in all different ways, okay? But all the E's that we started with were used and converted and didn't just disappear, okay? They got changed, but not used up by the universe, okay? So they're still there. In that scenario, the potential energy was the chemical energy, and the kinetic was pretty much everything else. Even thermal energy counts as kinetic because it is really about how fast particles are moving, right? So that's kinetics. Okay. So potential energy in terms of chemistry is usually thought about as chemical bonds. Okay, and so what's a bond? Well, so for example, in our food, you have carbon-carbon bonds. That's the most common type of molecule in our food. Carbon-carbon bonds are pretty high energy, and that energy is because the electrons are essentially squished in between the two carbons. So when we get to Lewis dot structures, we're going to learn that you can draw the electrons in a bond like this, and it sort of demonstrates that these two carbons are sharing those electrons. And so the two carbon atoms have to be kind of close together to do that. And so a chemical bond is really like a compressed spring just kind of waiting to snap open. And as it turns out, in order to have a bond, it requires energy to break it, right? So a compressed spring stuck between two objects isn't going to suddenly just come out of that situation. It's kind of stuck. In order to get it to come out, you have to flip a switch or move one of the objects in some fashion, and then the spring can release the energy. So chemical bonds are the same way. What this means is in order, you have to push a button, you have to release something, you have to move something. So in order to break a chemical bond, you must put energy in. That means it never produces energy. Oops, that's supposed to say always. I don't know what just happened there. There we go. So in order to break a bond, we always have to put energy into the bond. It never gets us energy out, okay? So then how come chemical reactions occur at all? Well, the answer to that is that when a reaction happens, we have to put energy in to break the bonds that are present in the reactants, but we get energy back when we make new bonds, okay? Particularly when the new bonds you make are inherently lower in energy. That means the difference between the bonds formed and the bonds you broke is extra energy that gets released in the form of heat or light or sound. Okay, so then the question is, where does this energy come from? When we did the chemical reactions in lab, you didn't have to heat it up. You know, nothing sort of looked like it was going into the reaction besides the two like pieces of matter that reacted. And the answer to that is that it comes from the universe, right? So we live in a universe where there is always particles with energy. And so, because nothing can get to absolute zero. And so the energy to do a chemical reaction comes from the environment around the reaction, the air, the test tube, whatever, your hand, you know, your hand was touching it. And so the heat from the environment is what causes the bonds to break, okay? Unless, of course, it's a reaction where you actually add the heat yourself. That happens also. But in all those cases, the energy is conserved. So in other words, if we think about this as a little diagram where we have energy and our reaction progress on the bottom. If I start here with my reactants, so relatively high in energy, I have to put a little bit of energy in to get them to do anything. But then after I do, quite frequently, we see that their products have a lower amount of energy. So this change in energy is positive. I'm sorry. It would not be positive. So if we said this was, 10 joules, like 10 energy units, this would be lower. So it's 5. And a delta always means final minus initial. So E final minus E initial. And so our final here was 5 minus our initial is 10. So we'd have like a negative 5 joules happening here. So this change in energy is negative, which means that energy is going out of the system, and it's going to come out of the system in the form of heat, light, sound. Those are the main types of energy that chemicals can generate. Okay. Either way, though, if we add up all of that kind of energy that might be emitted and the energy of the bonds that we have at the end, it's going to equal the energy that we'd start with. Okay, so in thinking about kinetic energy, the other kind of energy, we can envision 2 different scenarios. Okay, so one where you, my wonderful class, is sitting at the top of a hill and you have a beach ball and a bowling ball, and I am at the bottom of the hill and you would never want to injure me, of course. So if you roll those balls down the hill and I had to choose one of them to avoid, thereby being hit by the other one, of course I would choose to be hit by the bowling ball. I hope you all know that, right? Because of course the bowling ball has a lower mass. And so I know that it's not going to hurt me as much, hardly at all, right? But whereas a bowling ball rolling down a hill could probably like break a bone or something. So I try to choose the one with a lower mass. Now this is a situation where both objects are moving at a reasonable speed. They're moving at the same speed, the speed of gravity, 9.8 meters per second squared. If we change the scenario and we make that beach ball move closer to the speed of light, which is 2.9 times 10 to the 8 meters per second, so it's very, very fast. If the beach ball was going really, really fast, I would prefer to avoid that one because it's obviously going to hurt more. There is a really interesting piece in a book that I have written by a physicist who is also a comic writer. It's called XKCD What If is the name of the book. And in the book, somebody proposes the idea of throwing a baseball near the speed of light and what would happen to the world. And the answer is, even if you had somebody talented or lucky enough to hit the ball, it's not a good situation for anybody because the impact of something moving that quickly hitting another object would cause essentially a ripple effect where the entire world, actually the universe, gets destroyed because it's such a high energy collision. So if I have to avoid one or the other, I am going to avoid the beach ball because it is moving so, so fast that it will destroy the universe if it hits me. Okay. So then is the mass or the velocity, the speed, more important here? And so the answer to that is the speed, right? So when the 2 objects were moving at the same speed, I chose mass. But when they're not moving at the same speed, we try to avoid the thing that is going faster. Okay? The same way that if you had to choose between getting hit by someone on a bicycle or somebody in a car, you were definitely going to get hit by the bicycle. Well, also they weigh different amounts, but still, you get the point. Okay? So speed matters more, and that's because the formula for kinetic energy is 1/2 times mass times the velocity squared. So this mathematical term here is the key. If we square velocity, that means the velocity has a much bigger influence on total energy than the mass does. Now they're both important, right? But velocity matters more because it's squared. Okay, so there's your equation. So when we think about another kind of energy, electrical energy, we know some stuff about that already. We know that opposite charges attract each other. So what we mean by that is literally that when they get closer together, they each mutually have a lower energy. than when they were farther apart. If you've ever been in a long distance relationship, you might understand this idea, right? But so the reason a magnet suddenly just snaps to a refrigerator when you get it close enough is because the energy is lower when those two oppositely charged particles are close together. Okay, so we get a reduction in energy. Now, if we had two charges that were the same, say two positive charges, and they're initially really, really far apart, and then they get closer and closer together, say like positive charge here, and they get closer and closer, and suddenly they're like here, there comes a point where they have such high energy, right, that they repel each other. So you can kind of graph this, right? So here's our energy graph. It's a little crooked. Energy here, and distance on, so energy is vertical, and it's getting bigger that way, and the distance is the center axis here. And so what happens is, as two positively charged particles get closer and closer together, their energy goes up and up and up and up and up and up and up, and they don't, you know, they don't want to be really close together. If two oppositely charged particles get closer and closer together, you actually see the opposite thing happen. We'll make blue our opposite charges. So if two similar charges are getting together, it means that their energies, as the distance gets smaller and smaller and smaller, their energies are going to get closer and closer together, right? So these are our two oppositely charged particles. Here's our negative, here's our positive. As they get closer and closer, so that distance between them is smaller, the energy becomes closer and closer to our middle line here, which is 0. This is an attraction. That's what we call an attraction. A repulsion is the opposite, where the energy gets way too high and the two objects fly away from each other. Okay. So this is described by this equation, where K is a constant and our charge is here. So positive 1 or negative 1 are the only charges we really have, right? Protons and neutrons. Sorry, that was wrong. Protons and electrons. And so if we have positive and positive here, our electrical energy would be positive, right? So it's like 1 times plus 1 divided by whatever the distance is. If the distance is really big, that positive number would be a very small value, so not a very significant force. But if this distance is very small, then we're dividing by a small number. So we have a very large positive energy. That's not favorable. Energies that are lower are favorable. So if we have like a positive 1 and a minus 1 here, then you're going to have a negative energy, and the smaller the distance, the closer together they are, anyway, in other words, means that the energy is going to be larger and negative. That is good. So negative energy means lower overall. And nature likes energy to be lower. It's sort of the way things go, right? Okay. So this leads us to a few equations so far. And in this exam in particular, in this chapter in particular, we have a lot of equations. So I'm going to keep summarizing as we go along. Okay. So the last thing I want to talk about in this video, there's going to be more to come, so don't worry, is units. Okay, so we have a couple of units. We've talked about this in class already. The most common is the joule, which is essentially like the metric unit of energy. It actually has a definition based on our primary base units in the metric system. So this is a handy thing to know, especially when you take physics, because no one ever explained this to me. We had to deduce it eventually. I'm giving this to you for free, just so you know it. A joule is defined as kilograms times velocity squared, right? Because it's energy, kinetic energy, mass times velocity squared. So that's where these units come from, okay? So we also have another unit which was developed classically, which means out of convenience more than from the metric system. So the calorie is defined very specifically as the amount of energy you need to change 1 gram of water by 1 degree Celsius. Okay. The conversion between joules and calories is provided to you here. So this is a dimensional analysis thing. right? So 1 calorie is the same as 4.184 joules. So I can use this to either get calories, which would be the one that I just wrote on the left, or to get joules. Okay, now here's a caveat. There's something we need to know. Our labels, nutrition labels with for food, are wrong. When they say calorie, they make it a capital C, and that's how they get away with not labeling it as what it actually is, which is kilocalories. So if a Snickers bar says that it's 260 calories, that's what we consider as nutritional calories because it came from a nutritional label. What that means is it's actually, so nutritional means kilocalories, so I'm gonna write that. It's actually 1,000 times bigger than that, right? So the energy present in a Snickers bar is 260,000 regular scientific calories as defined right here. That sounds shocking. It's a lot. And that's why marketing companies changed it to kcals. Okay. So take a second and answer the question in the learning module and then resume the next video.